Let me close these.
1.1, that's just...
You okay?
It's the mole. And then you multiply that by the Avogadro's number.
Hot day? Okay.
It's the one you have to memorize. No, 8.31, that's the R. Avogadro's number is the one we use in chemistry. During the first few lessons, we were 6.67 times 10 to the power minus 6. That's the one.
Now, the next one here, hey, got it? No, next one here, A part. So this one here, next question, number 2, yeah. 4 assumptions of ideal gas law. So it's one of these things that I've said a little bit in class, and maybe Lorraine says it too, but you can't always use the ideal gas law. Like, it works in most situations, but the key word in the law is this word here, ideal. So the question says, name or give 4 assumptions for the ideal gas law. Now, I was just checking what they have in the marking scheme, and it might be a bit different than what you give in different books. But can anybody think of the 4, if you know it, 4 things you would need to have so that you can use the ideal gas law? So this might be a bit tricky, but I'll help you out. The first thing is that the force between the atoms or the particles or the molecules is small. Okay? I mean, that the particles, they don't really interact so much, is what I'm saying here. The second thing is that the ideal gas law really works well when the density is small, but it doesn't work so well when the density becomes really large. And in fact, it doesn't work at all when it's not a gas, when it becomes a solid or a liquid or something like this. So you need the density to be small. Okay? Sure, let's look at what they gave here. The force is small. That's not great. The volume of the molecules is small compared to the volume of the container. So in other words, the density is small, that there's lots of empty space. That's the second one.
The forces between particles?
Particles is small. Sorry about that. The time occupied by collisions is negligible compared to the time between collisions. So another way of saying that is particles collide infrequently, that there's not too many collisions. Not too many collisions. And then the last one, let me try and get it for you. Oh yeah. No acceleration. So when your particles are moving around, they're not accelerating, they're just moving at a constant speed like balls bouncing around. Now this is, I think, the only time I've seen this in the exam, okay? And it is actually kind of difficult because it's one of those things you have to learn off. Will it come up in the exam? It could. But the ones that should be easy to remember is
No acceleration.
no acceleration, low density, low force. But if you look at this one is really almost the same as the last one. Because after all, force equals mass by acceleration. So there's not a huge difference between the first one and the last one. Density is small just means your gas is spread out, that's not really high pressure. But that's the other thing, density is small. Another way I could say that is it's not high pressure, you know. So there's different ways to write it, but the way you're thinking about an ideal gas is it's a nice, lots of empty space, nice and big, lots of empty space. The particles aren't colliding too much. There's not like there's a big force pulling them somewhere. It's all just kind of simply moving around. Okay, so that's A. Can I scroll down? Yep. And like I said, if you check a physics book or a chemistry book, you very well might get different answers. But I think the answer that would be in common to all books and all notes would be definitely the first and the second. I mean, that's going to be pretty universal. But how you phrase 3 and 4 might be different, okay? Right, B part now. A cylinder contains 1.5 moles at a temperature of 20 Celsius, so I have to add 273 to that, and at a pressure of 1.2 megapascals. Happy days. What is the volume? So PV equals nRT, V equals nRT over P. Go.
.045 times 10 to the minus 3.
Yeah? Seems very small, but that's the answer you got? It's probably just a small little container. You got that too, Ali?
Yeah.
Yep. Great, okay. What is the number of molecules? Again, easy peasy. How many moles do I have? 1.5 moles. So if I want to go from moles to molecules, what do I do?
Right.
Multiply. You're thinking of mass. Multiply by Avogadro, so tell me what you get.
9.03 times 10 to the 23.
Okay. If the molar mass is 28 grams, what's the mass of the cylinder? So the molar mass is 28 grams. And how many moles do we have?
1.5.
And you know how to multiply.
0.0.
Even if you don't, you have calculators. So what did you get?
0.042.
42 kilograms. See, it's really not that difficult, this question.
If you're a physics teacher.
No, it's not that difficult if you're a physics or chemistry teacher or student. Or even if you're a Brendan. Sorry. I should really pick on people who aren't here. Or even if you're a Kurdi.
Yeah.
Fine. Gotta turn to Eeyore.
That's okay. Everybody loves ER anyways. Determine the volume that the same mass of nitrogen would occupy if the temperature was 0 and the pressure was that. So now everything stays the same. Well, no, sorry. The temperature changes and the pressure changes. What's the volume? So what's the formula for volume? It was V equals nRT over P. The N is still the same. The R is still the same. Now the temperature is 0 Celsius and now the pressure is 1.01 times 10 to the 5. So they would like to know what is the volume now. So what's the volume for this one?
0.0336.
Yeah.
Now, see that part there? That was part B of the question. How many marks do you think for that? Now, have a look at it. How many marks do you think for that?
10?
4, 5,
10.
10.
10.
See, I don't have to guess.
Good for you. So there's 10 marks for that, all right? So ideal gas law, okay, should be doing it in the exam, 10 marks. And there was only one formula I really used for all of those. PV equals nRT.
Wait, for the last question, where did we get that pressure value?
It's given.
Oh, it's good.
It's served up to you. You know, 10 marks on a plate. Here, take it,
I like
please.
this question.
Yeah, it's good.
Please, can you show me the previous one?
Which one? That one?
Yeah, the previous.
Yeah.
Just 1.5 minus 0.4.
Yeah. Oh, you asked me this already. Look, this tank has 1.5 moles in it.
Yeah,
And then some of it leaves,
okay.
and it's left with 0.4. How much has escaped?
So the difference.
Yes.
So it is 1.1.
Oh, it is.
Error.
Yeah. Mathematical error. You're right. Sorry. No, nobody else said this. 1.1, not 0.9.
4.4 times 10 to the minus 3.
Oh, it's one of those days, is it? What is it? 4.4
Times 10 to the minus 3.
times minus 3. All right. Well, it started off with me having the lens cap on the projector, so
So yeah.
yeah. All right, C part now for this. Can I scroll down? Yeah. Okay, C part. A well-insulated copper container of mass 0.3. So you got a copper tank. Its mass is 0.3 kilograms. It contains a mixture of ice and water of 0.8 kilograms. So inside here is ice and water. Let me draw that again. So there's some water and then there's some ice. And this is at temperature 0 Celsius and its mass is 0.8 kilograms for both the ice and the water together, okay? Now, heat is supplied to the container at 750 watts. So 750 watts, that's 750 joules per second. So every second there's 750 joules going into this container. After 5 minutes, the temperature of the container and its contents is 25 Celsius. So then 5 minutes later, everything is, 25 Celsius. So, they want to know what was the mass of the ice at the start. Okay? So, I'll wait for you to write that down. Can I start it now?
Yeah.
Now, first thing we should do is we should work out how much energy this received. So how much energy does it get per second? 750. And for how long is it getting it? 5 minutes. So you need to do 750 multiply 5 multiply 60. So what's that then?
5,000.
22500? Like this?
Also.
3 zeros, yeah?
Yeah, I
Okay.
multiply 60 by 5.
By 750, yeah.
Yeah.
Yeah, that's it. So that's how much energy it got in total. Okay? Now, at the very end, all of these three things have turned into 25 Celsius. So
This is question 3, yeah?
this is number 2, the last part of it, part C. Okay. So let's look at the copper first. How much energy does it need? Well, what's its temperature at the beginning? Did I say?
0 degrees.
Wouldn't it be the same, yeah?
Same as the water
Is
and
it?
the ice.
Yeah, it would be, wouldn't it? Yeah, so everything is 0 degrees. Okay. So how much energy did it get? Well, the formula is mc delta T. So that's M. C they give you is 420. And then what's the delta T for the copper? How much temperature did it gain? 25. Yeah? Okay. Now for the water, again, M, but what's the mass of the water? We don't know. So let me call it just X. M, C, and the delta T? What's the delta T? 25. Okay?
Shouldn't be out in Kelvin or Celsius.
No, it's okay. We can leave it like this. Now we have to do the ice. Please be careful. The ice must do two things. First, it must convert from ice to water. So what's the formula for that? Do you remember?
ml.
ml. Now, we know the L. He gives it to us. It is quite a large number. 3.3 times 10 to the 5. But do we know the mass of the ice? No, we don't. But what's the mass of the water and the ice? 0.8. And what's the mass of the water? I called it X. So what would be the mass of the ice then?
0.8 minus X.
Good. Now I'm going to squeeze this in underneath. Yeah.
There's 420 on the left-hand side and 4,200.
Yeah, this is the copper.
Oh, that's just the copper.
Yeah.
Okay.
Copper,
That's water.
water, ice, and then the ice turns into water, and that too needs energy. So again, it's M, C, delta T.
I can't see.
Do you need me to zoom in, or? Now, once you write that down, you can just multiply it out and solve for X. So we'll just get Derive to solve it to save time here.
Can I go to the bathroom?
Yep. Okay. Do you understand how I formed that equation? Because that's the key thing here, is forming that equation. Actually, once you have the equation written, then it's just a matter of solving it. So, Brendan, can you call out the equation? I'll type it in here. Did you write it down?
From the beginning, yeah.
Yeah.
2.25 times 10 to the power of 5
Yeah.
is equal to 0.3 times 420 times 25
Uh-huh.
plus X
Mm-hmm.
times 4,200 times 25
Mm-hmm.
plus 3.3 times 10 to the power of 5 times 0.8 minus X
Mm-hmm.
plus 0.8 minus X
Mm-hmm.
times 4,200
Mm-hmm.
times 25.
Solve expression. We'll go numbers, real, solve. So that's X, which is the mass of the water. Okay? But he wants the ice. So I'll just do,
0.8.
yep, 0.8 minus 0.3822. So about 418, 0.418. So the mass of the ice equals 0.418 kilograms. Now, look at that. How many marks do you think for that part? Now remember, the last part, I didn't tell you the marks, but how many marks do you think for that?
Just C.
Yeah, just what's on the board.
About 5.
You're not too far off, but it's better for you, it's 6. But, you know, like I said, what have I really done? I've written down one equation and I solved it. 6 marks. Do you get what I'm saying? If you just keep your head cool and stay focused and practice some of these, you should be getting good marks in the exam, okay? There's no excuses for not getting good marks.
X is water, right?
X is water, yeah.
Then
I-
what about ice?
Because he asked for ice, actually. It would have been better if I called ice X. But I didn't read that when I was writing the equation down. Is that okay? Yep. Oh, okay.
How we can solve it with calculator?
No, you have to do it like you did in maths class. So you have to multiply it out, group things together, divide, etc. I'm just cutting out those steps because that's not what the physics is about. Okay.